and we are Team FarSounder. Who is FarSounder? FarSounder creates a 3D forward-looking sonar that allows the user to measure the depth of the water in front of them up to 50 meters deep. FarSounder transmits a signal, an acoustic pulse, through the water and measures the time it takes and uses the data. Oh, sorry. Who is FarSounder? FarSounder creates a 3D forward-looking sonar that allows the user to measure the depth of the water in front of them up to 50 meters deep. FarSounder transmits an acoustic pulse underwater and then uses a array of sensors to measure the echo. FarSounder then takes this signal and data processes into a 3D image like the one you see above. In this image, you can see this is where the boat would be, and this is the actual obstacle that the FarSounder detected. During the time it takes to transmit and receive the signal, the boat has the opportunity to roll and pitch. This is where the roll and pitch sensor comes into play. The roll and pitch sensor measures the roll and pitch of the boat and offsets the data accordingly for a more accurate measurement of the object. Right now, FarSounder's existing sensor is dated. It's relatively costly versus other motion sensors on the market today. It takes time to install, and also it takes up too much space in the actual transducer module itself. Our goal was to create a smaller, more cost-effective solution that can fit right onto the data acquisition board inside the transducer module while measuring roll and pitch with a certain degree of accuracy. I'm happy to announce that the team has successfully met their best anticipated outcome. FarSounder will be able to save space, time, and money in the near future. Some key accomplishments that helped us get to this point was with the printed circuit board, the filtering algorithm, the script to actually calculate roll and pitch, and the mounting board and the boat test. The first key accomplishment was the printed circuit board. The printed circuit board had the same exact form factor as the existing sensor. This allowed the team to implement the PCB inside the transducer module in the exact location where the existing sensor was housed. The purpose of the PCB is to measure 4 different inertial measurement units in the same environment at the same time. From there, we can take the best sensor and integrate it onto the data acquisition board inside the transducer module. As you can see, this is the exact form of the existing sensor, and this would be the form of one of our new sensors, a dramatic decrease in size from inches to millimeters. We successfully integrated all 4 IMUs onto the PCB and communicated using I2C and SPI. We also successfully integrated a sensor select. When the PCB is inside the transducer module, the user can select which sensor is communicating to the data acquisition board using the right 2 pins on the screen header. When the PCB is outside of the transducer module, the user can select which sensor is communicating to the PC using the dip switch located on our board. The point of the sensor select is to be able to select which sensor is communicating to either the data acquisition board or the PC in real time to make it easier for testing. Now I hand it to Cole to talk more about our project.
So probably one of the biggest difficulties that the team faced in the project was the debugging of the PCB. That would be because there were both hardware and software issues that needed to be solved, and the reason why it was so difficult is because in order to resolve these issues, a complete understanding of each one of the sensors is required in order to find the very minute details that were causing these issues. So through a lot of research, work, and help from our technical director, we were able to resolve many of these issues. So another aspect of the project was a mounting board to be used for a boat test. So for this mounting board, we utilized the evaluation boards and evaluation software that were provided by each of the different sensor manufacturers from our 4 chosen sensors. We use these to reliably log data from each of the sensors, and we could use that log data to compare to the log data of the existing sensor, which is the one all the way on the right on the mount. So we used this on a boat test. We went on the URI research vessel Captain Bert, where we got about 5 hours worth of sensor data from each of the sensors, and we had achieved initial data processing and analysis on all of the log data. But due to the completion of the PCB aspect of the project, we determined that this test should be repeated instead with the PCB solution for more confident comparison of the sensors. So for the software side, we basically just wanted to have an Arduino script that would do everything for the user. So the first step was to take the raw accelerometer and gyroscope data from the chosen sensor and convert it into roll and pitch, because it doesn't provide that right off the bat. So when we had done that, we were noticing that it wasn't very accurate. As you can see up here, there's a very large drift compared to the reference data of the existing sensor. And this is due to the associated drift that comes with gyroscope data. So we needed some sort of way to filter that data into more accurate roll and pitch information. So our solution for that was a complementary filter, which basically just weighs and combines the data from the accelerometer and the gyroscope within the IMU together to provide much more accurate roll and pitch information. So once we had that filter, we put it all into an Arduino script. The flow of the script was that given the selected sensor, we would take raw data from the accelerometer and the gyroscope. We would convert that data into roll and pitch, filter it, and then we would spit out that information in the exact same format as the existing sensor, essentially mimicking it. And here's what we found. This is a short comparison between what we have determined to be the best out of the 4 sensors with the existing sensor. So there's a roll maneuver, a pitch maneuver, a more complicated roll and pitch maneuver together. So as you can see, the chosen sensor matches up very nicely with the existing sensor's data. So this proves that we have found a comparable solution to the existing sensor in an IMU, thus achieving our outcome. And with that, there is a little more further work for actual field deployment of this sensor, and it is essentially just more testing to be completely confident in the choice of sensor that FarSounder will choose to go within their transducer module, and this would be in both controlled test environments as well as real-world test environments. So we would like to finally thank everyone who helped us to complete this project.